Hello, and thank you for coming to my GSA presentation on regularly spaced ridges of silicic lava flows and implications for inferring the rheological properties of planetary landforms. So first, I wanted to get started with what are topographic ridges? Well, they are often referred to as ogives or pressure ridges, and they refer to these sort of parabolic, laterally discontinuous ridges like we could see here on this Namekir or Salt Glacier at the Zagros Mountains of Iran, or even sometimes on other planetary bodies like this image from Barr and Proust 2010, which shows pressure ridges on the south pole of Enceladus. But most topographic ridges are clearly visible on the surfaces of lava flows, in particular silicic lava flows like Obsidian Dome, here in the Mono Inyo craters of eastern California, or across Cerro Chao in Chile. And the reason we care about these ridges so much is because in 1980, Jonathan Fink looked at ridges on Glass Mountain at Medicine Lake Volcano in Northern California and essentially made them analogous to pohoihoi ropes of basalt in Kilauea, and was able to extract viscosity information about this silicic lava using the fold theory he developed for the pohoihoi. And so Fink's theory is based on Biot's 1961 fold theory, and it relies on essentially three different variables. The first is the stress ratio, which is pretty elegant. It's a ratio of the normal or gravitational stresses to the viscous compressive stresses. And you can kind of think of this: if the compressive stress is too low, if it's the strain rate's too low, then these ridges would essentially just dissipate as gravity pulls them down. The second and third variables are the viscosity ratio and the dominant wavelength. And the viscosity ratio refers to the difference in viscosity between the surface and the interior of the lava. You'd picture the surface being cool and the interior being warm, and that creating a viscosity contrast which promotes folding. And all you need to determine these three variables are morphology. So you've got wavelength, fold arc length, and layer thickness. And this is the theory that allows us to infer rheology from the morphology of these lavas. But there's been some problems with recent studies in these rheological estimates. For instance, Deerdorf et al. In 2019 used discrete Fourier transforms to measure the wavelengths of a wide compositional range of lavas in Oregon. And what they found was a lot of overlap in their dominant wavelengths until you get to basaltic pohoihoi, and then a radical change in wavelength over a very narrow range in silica content. And James Farrell and others at the Syracuse Lava Flow Project actually created some synthetic pohoihoi lava, created some digital elevation models, or DEMs, and then used those folds to infer the rheology. And as you can see, the folding model does not match other leading models of for viscosity like the Giordano, Russell, and Dingwell models. And an even more recent paper has actually suggested that the ridges on the tops of silicic lavas are actually formed from extension, not compression, invalidating the folding model. And the evidence they used for this paper was a robust field study where they looked at these medium scale folds that are always cross-cut by younger brittle fractures, and did some structural mapping and performed some simple surface reconstructions, and found that the extension fracturing paradigm was a much simpler restoration process than for the compression and folding paradigm, requiring much lower finite strains and overall a much simpler explanation. And if you want to learn more about this study, my advisor will be giving a presentation on Monday, October 26th at 5:30 p.m. in the general volcanology session. But for our study, we were curious if we could use the morphology of these ogives to determine whether or not they formed under compression or extension. And if the ogives form from extension, what does that tell us about the rheology of the underlying material? So in order to answer this question, we collected a suite of digital elevation models from basalt pohoihoi lavas that we know form in compression to compare to a couple of blocky lava flows that might have formed under extension. Then we performed some discrete Fourier transforms on the surface of these topographic ridges so that we could compare amplitude, wavelengths, and number of peaks. And so for an example of what of our Pohoihoi DEMs might look like, this is a section from the 1969-1974 Manaulu eruption. We used ground-based photogrammetry, and you can see a nice trail of Pohoihoi ropes going right down through the center of this, this point cloud here. For our blocky ridged lavas, this DEM came courtesy of Brett Cart, the USGS, and again you can see that this is, even though this is a basalt lava, it's still blocky. And you can see ridges and troughs that are indicative of these ogives, or pressure ridge features. And Brett used a drone to collect this data. And lastly, we had a bunch of high-resolution DEMs that were collected as part of Tyler Leggett's master's thesis at Baylor University, including segments from Obsidian Dome and South Cooley. And this one here is, you can see on South Cooley, and it's, yeah. So if we take our DEMs, the next thing we need to do is to analyze them for their discrete Fourier transforms using Welch's method, which has been shown to be ideal for noisy natural data sets. The first step in our algorithm is to normalize the topography. So here you can see a topographic profile that corresponds with this line here. And you can see it has some underlying slope, so we need to remove that. We used a second order polynomial, and this is the result. These are vertically exaggerated, which is why they look so dramatic. And then once the topography is corrected, we can perform the discrete Fourier transform, and it produces a power spectrum density plot like this, which has an underlying power law baseline, which we could remove, and we get a plot that looks like this with normalized power amplitude, which corresponds to sort of signal strength, and wavelength on the x-axis, so that we can determine what the dominant wavelength is across these ridges. So here's a summary of our results. We have our Pohoihoi lava on the left, and then our blocky lavas on the right from the Galapagos basalt and South Cooley rhyolite. The upper panel in these figures are the normalized topography, so you can see how variable the topography is across the DEM. Each black line corresponds to a single row across our DEM. And then this lower panel here is our normalized power spectrum density plots as a function of wavelength. And again, each black line corresponds to the results from a single transect across the DEM. And what we can see first in the topography is that the ridges of the Pohoihoi tend to be rounded, and that's what you'd expect for folding of an upper surface. But we don't see nice rounded ridge tops for rhyolites, or even to a lesser extent the blocky So that's the first sign that there's some difference between the Pohoihoi and the blocky lavas. The second line of evidence is that if we look at the amplitudes for the power spectrum density plots, Pohoihois have generally much higher normalized amplitudes than we'd see for the blocky lavas. And we're interpreting that to mean that the signal strength is just much lower for blocky lavas when compared to the Pohoihois. And then the third line of evidence is that for the Pohoihois, we have two very distinct peaks that exist, whereas with the blocky lavas, we get sort of either a diffuse, broad peak, or even sort of a compound peak that are sort of indistinguishable. And this is likely due to variations along the length of the DEM. So with these lines of evidence, we think preliminarily that we know Pohoihoi forms in compression, but maybe these blocky lavas are forming from extension. But what we really need to test is unequivocal extensional terrain to compare to. And the best terrain I could think of is the Basin and Range in the western United States. You can see a DEM here generated using the Shuttle Radar Topography mission. And again, we applied the same analysis, and we see pointed ridges, no rounded ridges. We can't see the troughs because they're obscured by sedimentation, but we're really focused on the ridge tops, not the troughs in this case. And again, if we look at the power spectrum density plot, we see a nice broad, tall peak that is pretty diffuse. And again, the amplitudes are much lower. And this, we think, is very comparable to what we see with the blocky rhyolite lavas, suggesting that the blocky lavas are forming an extension, not compression. So if they're forming an extension rather than compression, what does that mean for the rheology? Well, instead of representing a viscosity contrast between a brittle upper layer and a ductile interior layer, we propose that the ridge spacing is actually a function of the depth to the brittle ductile transition. So for instance, in the basin and range, the average crustal thickness is between 15 and 20 kilometers, and the dominant wavelength that we measured is about 30 kilometers, suggesting that the dominant wavelengths are roughly 2 times the crustal thickness, and that could be used to interpret various things on the surface of planetary landforms. So with that, I'll leave you with some conclusions. We've got topographic ridges from blocky lavas are more similar to basin and range than pohoihoi lavas, suggesting ridges on blocky lavas form an extension. The folding model cannot be used for ridges formed by extension, only compression, so you need to be careful when you're applying the Fink folding model. And 3, regularly spaced ridges on the surfaces of blocky lavas are likely controlled by the depth to the brittle ductile transition, rather than a viscosity contrast in the upper surface and the interior. And with that, I'll take any questions. Thank you.